So I was encouraging you guys to ask questions. So if you are not asking questions, let me ask you a question. I want everybody to participate in this so that the topic that we're going to study, it will remain with you for the lifetime. Okay. So let's suppose you are traveling in a car. So when you are traveling in that car, you suddenly see the speedometer. Okay. So there is that speedometer. Let's suppose it looks something like this. There are numbers written over here. So you read some stuff from them. You have a reading on this. Probably this is an analog, or maybe today we have digital speedometers where we'll say, let's suppose 40 kilometers per hour, something like this. So what is the idea that you get out of this? Anyone can answer. So whenever you look at it, so what do you mean by this? Because things have meaning associated with it. So when you look at the speedometer, so it reads, let's suppose 40 kilometers per hour. So what do you mean by this? So what do you understand by this even? Anybody? कोई भी बोलो. Mahmood, what do you understand by this?
It means that after 1 hour we would have traveled around 40 kilometers.
Okay.
If you will go same, then within 1 hours we cover 40 kilometers.
Right. Okay, okay. A good explanation. So if you see these sort of things, they're aesthetically change. Okay. So something is changing. Let's suppose you read at one instant you read 40 kilometers, then the second instant you read 50 kilometers. So, but you know that these things are instantaneous, and this is not guarantee that if you assume that I'll cover 40 kilometers 1 hour, there is an assumption again that you will continuously have this much of speed. Okay, speed basically is made up of two quantities if you see. Okay, speed is somewhat a function. It's a function. What's the function? It's the function of distance traveled and time. Okay, there is time, there is distance. Then from these two quantities, speed comes. Okay, so somehow this distance is related to speed. Okay, so mathematically, how we can see it? It's a function basically. There is some function, some association, some relation. So how do we define the speed? We say that okay, how much distance did I travel? How much distance will I travel in how much time? The distance traveled per unit time. So in 1 unit time, how much distance will I travel? So I label this as speed. So this is what I read on that speedometer. But if you see this distance traveled, okay, for this there should be two timestamps. Okay, so I'll start from somewhere. Let's suppose I'll start at 1 p.m. Let's suppose I'll see at 2 p.m. how much distance have I covered. Then only I can compute speed. So, but if you see the speedometer, directly you get speed there. So isn't it an oxymoron? Don't you feel something paradoxical going there? Okay, speedometer is showing me wrong. Because how we define speed basically is the distance traveled per unit time. Okay, if it is showing me something called as instantaneous velocity, instantaneous speed, there is nothing like instantaneous speed. Okay, so if we define speed, that we define speed like this: how much distance was traveled per unit time. So first we have to have a unit of time. Okay, that is where we study about change. Okay, now we have a function. We see how these functions are changing. So I'll have a heading of this. I'll call it an average rate of change. So why did I ask you this question? Because we'll see that how mathematics is being used, how we people are being manipulated, and the things that we probably never put a thought on. Okay, how is the speedometer designed? How does it calculate the things? Okay, so that thing basically has really some big philosophies, big mathematics behind that. So for that, we'll first have to go through this average rate of change. So now we have a function. We know what functions are. Functions are nothing but some machines which take some input and we get some output out of that. Okay, so now taking this example of speed, let's suppose we have this graph. I said that we can represent functions in different ways. There is a verbal way where I can just verbally communicate to you what is a function, and I can have an algebraic expression mentioning the function. But the best way is I'll tell you a story. So how I'll tell a story? I'll make a graph. Okay, this is the origin. Let's suppose 0. Let's suppose this is 1 p.m. This is 2. This is 3, and this is 4 p.m. Okay, and then I'll have some distance traveled. Let's suppose I'll have some. This is my time. Let's say on this axis I'm drawing the time, And now here I'll have, let's suppose, miles, distance covered basically in miles. So here for this one, let's suppose I'll have 1 point over here. So let's suppose this is 100. Okay, 100 miles. Then let's suppose on this 2 I'll have some 150 miles, and then this is 150 miles on this 2, and on this 3 let's suppose we'll have 200 miles. Markings can be here and there, but it's all right. Okay, now if I just make this graph, so this graph will look something like this. Distance is always increasing, something like this. May not be perfect, but it's all right. So here if you see this graph, okay, I'll just make this line a little bit darker so that everybody is able to see it. This graph tells you a story. So this tells you a story that a person started driving from this instant, let's suppose at a time which we'll call it 0, and let's suppose this is 12 and this is 1, 2, 3 and 4. Then if you see this graph, okay, after this much, let's suppose we'll measure the change from here to here. We'll measure the change from 1 p.m. to 2 p.m. let's suppose. Okay, how will we measure the change? We'll see that from this 1 to 2, 1 hour passed, 1 घंटा हुआ, उसमें हमने कितना डिस्टेंस ट्रैवल किया. सो हाउ मच डिस्टेंस डिड वी ट्रैवल? तो 1 पे हमने कितना डिस्टेंस ट्रैवल किया था, दिस 100, और 2 पे हमने 50 माइल्स, यहाँ पे 50 हमने ट्रैवल किया. Okay, so this much is the distance traveled. So if you see, this is the distance traveled. So this is 50 miles. And in what time? In 1 hour. So if somebody tells me what is the speed of your car, so I'll say I can give you the average speed. So average speed was 50 miles per hour. So what does that mean? What does the meaning of average? By average, I mean that if I constantly had this speed, so if I constantly, the rate at which I was going, if I constantly had that for an hour, so I'll cover 50 miles. That you guys gave the answer. So the assumption there was I'll constantly go with that. But you know that speed will increase, decrease. It will have, let's suppose you will sometimes accelerate the car, sometimes you will decelerate the car, you'll have to apply brakes. Sometimes you will see a straight road and there is nobody there, so you will just accelerate the pedal and then you will slowly stop wherever you have to go. But you will continuously carry this. Now, if you see now from this 2 to 3, let's suppose. From this 2 to 3, let's suppose this is some other mile. Let's suppose we have some other value over here. This is 300. Some 300 value at this 4. So now in these 4 hours, let's suppose we have 1, 2, 3 and 4 hours. So in 4 hours, we had 300 by 4. Okay. Again, maybe what we can do is, so this value, let's suppose is 50 again. Huh? I don't think it's 50. So how much is 300 by 4? Some 70 something. Okay, let's suppose this is 70 something. You see that here we got more speed, and here if you see that we got 50 miles per hour. Here we got, let's suppose 72 or something, whatever it is. Okay, now you see that here the average speed that you saw in 4, if you compute the average speed in 4 hours, there you will see that value is different. Now if you compute the average speed in 1 hour, there you see the value is different. So what is this basically happening? What's happening there is the main concept that we are going to study is this. So if we change the time span, okay, so accordingly you will see the average is changing. So what is the average? Average is just a number. Average is the number which summarizes this thing. Okay, it gives a summary of a thing. तो अगर मैं कोई चीज का average बोलता हूँ, it doesn't mean that it will probably have the exact value, but what will it give? It will give a generic idea. So let's suppose हम यहाँ पे कितने लोग हैं, कभी किसी क्लास में हमारे पास 10 लोग होते हैं, कभी 20, कभी 50 लोग आते हैं, कभी let's suppose 30 आते हैं. So what we do is I'll tell you an idea. I'll tell you at average कितने लोग आते हैं. So this is an aggregate. It will give me some idea. So average basically tells me the tendency. So central tendency. So we'll see in depth what the averages are probably when we will read about statistics. But here what I want you to get is that these things, if they summarize a thing, they are basically defined over a change, over a period, and where some change happened. Okay, I'll go back to the example of speedometer. Please bear with me for probably few minutes so that we'll put these pieces together. So what I'm saying is that now we have computed some average. So speed was there something, and I want to compute an average. So if I compute the average rate of change, average rate of change of distance. So this is giving me speed. So okay, this thing gives me speed. So you can compute average rate of change for any function per se. Okay, if you are given any function, I just gave you a function. So there you can just compute this. So let's suppose you have covered 150 miles in 3 hours. So you got 50 miles per hour. So I gave you on time interval, I gave you the change in the distance. So distance traveled was 150 miles. So how to do this basically? So this is governed by a function. You know that distance traveled will be a function of time. So distance traveled is a function of time. Okay, so this is the function of time. Now, if this is a function of time, so what we will do is, so accordingly it will somehow have a relation or somehow have a function with the time. We probably, again, it won't be a causation. I am not speaking about cause. Time does not cause speed, or time does not cause distance. So what I am saying is, there is some relation between these two things. As the time passes, you are seeing that distance traveled it's getting more. So how do you compute this? Let's suppose I write this distance traveled something like this, s of x. This is a function. Okay, or s of t maybe. So t is time. So here if you see, this is time and this is my function. Okay, and I get the distance traveled. This is my function. So how I can write it? I'll write d is equal to s of t. Usually so far we were writing the things like f of x, y is equal to f of x. I just changed this notation. Syntactic sugar, nothing big thing. So if you see over here, so this d I have defined is s of t. So what is this telling me mathematically basically is that this distance is somewhat having a relation or a function, we call it, with the time. So now I'm saying that I want to compute the change. So I want to compute change. If I compute change, so from that I'll get speed. So if I'm computing change of this distance with the time, so I'll get speed. So here let's suppose we have a time instant t1 and after that we have t2. So if I say s of t2, so what will this give me? So this quantity over here, this will give me distance traveled till t2. Okay, I'll have this s of t1. So what will this give me? This will give me distance traveled at time t1. So what is the distance traveled at time t1? So as you say, I'll write an assumption, t1 is let's suppose less than t2. So we are at 1 p.m. and after that this is 2 p.m. So we'll have covered some distance. So till 1 p.m. we might have covered some distance, and after that we'll cover some more distance. We'll go till 2 p.m. So now if you see, I'm computing change. I'm saying s of t1, t2. So this will have some concrete value. S of t1 will have some value. I'll subtract these things. I'll just compute how much distance has been changed from 1 p.m. to 2 p.m. and then I'll divide it by the time, how much time it took to cover me this distance. Okay, so maybe I'll write t2 minus t1. So what this will give me basically is speed. How many of you understood the formulation? Because this is the basic crux of calculus. Okay, so this is just notation. If you are confused in the end, please do ask me. I'll just take an instant and I'll explain these notations. So s here is the function. I said that distance is somehow related to time. So mathematically, how do we write that? We write that in functions. So that is d is equal to s of t. You give a time and this s is some sort of a machine. It will give the distance traveled at that time, till that time. So I'm saying that, let's suppose now we have an interval. That's why I talked about interval. Okay, the interval basically is, so here we had time t1, we had time t2. So this was our 1 p.m. This was 2 p.m. Okay, we're covering some distance, we're driving a car. So there I said that, you know that this distance is somewhat related to, this is related to the time. Okay, so I defined that like this, s of t. So s of t basically is, give me an argument t over here, give me some value of the time, so I'll tell the distance. Okay, that you can clearly see it from here. So we made a graph also. To explain this, we made a graph. So let's suppose I'll give you 3 p.m. So you can just tell me the distance. Let's suppose 210 meters. I'll give you 4 p.m. You can see 300 meters. So these are the things that are given to me. This is basically our data. This is my data, and from the data I can clearly see that somehow this distance is related to time. So mathematically I wrote it like this: distance is equal to s of t. Okay. So initially I told you that we usually write something y is equal to f of x. So where we have a quantity x and where we have a quantity y, two quantities are dependent on each other. So what is the function? Function is the rule. It's a mapping which maps these quantities in some sort of manner. Okay, and then we'll give some value to x and some value of y will pop up from there. So that's why we call this variable as dependent variable. This value is dependent and this value is independent variable. Why? Because we are giving values to x and corresponding y is forced to get a value. So why is this called independent? Because you can give any value to this. Okay, and from the domain. Okay, once you give that value, then function forces the y to take a value. That's why this is called as independent variable. This is called as dependent variable. Coming back. So if you see, this distance is now somehow s of the time. So we wrote it d is equal to s of t. Again, just a notation, not a big thing. So I said I have to compute the change. So I'll compute the change. If I have to compute change, I said, let's suppose there are these two time instants, T1 and T2. This is 1 p.m. and this is 2 p.m. So now I'll have covered more distance at this 2 p.m. because this T2 is greater than T1. So let's suppose I covered 100 miles till here, and then till here I'll have covered 200 miles. I'll have covered one more 100 miles, that is 200 miles in total. Okay. So if I have to compute this change, so how to compute the change? I am saying I have to compute this change. So what I'll do is I'll give S of T2. So this will give me the distance traveled till T2 time. S of T1, this will give me the distance traveled till T1 time. This is distance traveled till time till 2 p.m. Distance traveled till 1 p.m. So now I want to see how much distance have I traveled in this interval. From this T1 to T2, how much distance have I traveled? So I traveled this much distance. I'll just see what was the value at this point minus value of this point. And then I want to see the change. So how I can figure out the change? I have to have a reference. What is the time I took? Okay, if I'm measuring a change, I'm changing, I'm seeing the distance is being changed. Okay, there is a change. Then okay, I want to quantify this change, like with how fast this change happened. Okay, how fast this change happened or how slow this change happened. So this is the change. Now if I want to see how fast or how slow this change happened, what was the rate of change? That's why it's called rate of change. It's not just called change, it's called rate of change. Okay, change is this. What is the rate of change? Rate of change is I have to have a reference. I have to have a reference from which I'll calculate it. So what is the reference? I'll see how much time I took. Okay, this thing basically rate of change, rate of distance with respect to time. I'll say change in distance with time is called as speed. So I'll call it as speed. How many of you understood the rate of change? Okay, now the thing is we have this rate of change with us. Okay, now what is the speedometer basically doing? It's again having this, it's again computing this rate of change, but what we call as instant rate of change. It computes instantaneous rate of change. Again, if you see that there is no change in an instant, so these two things did not match each other. If you see that, it makes no sense. There is no change at an instant. Why is it called an instantaneous change? So if you see something is changing, so you have to have a time duration. In terms of speed, you have to have a time, or maybe in terms of quantity, there should be some change should happen. But at an instant, there will be no change. How many of you agree that? So instant basically means there will be no change. By definition, that's the definition of instant. This happened instantaneously. By that I mean that there is no change basically. Okay. Now we had these some of paradox. We had to handle this. So this is the paradox of calculus. That's what gave birth to calculus. People have to compute this instantaneous change of things, instantaneous change of functions. Now let's suppose I was talking about speed only. Now there are a lot of things which will follow this pattern, where I'll have to compute this change. Okay. Now what mathematics does is, it will not only solve the problem of speed, it will solve the problem of all the things that fit in this. So it will say, okay, I have nothing to do with speed. So I have a function, let's call this y is equal to f of x. Okay, I have an interval, x1, x2. This is my interval. So I'll see what is the change in this interval. I'll probably write f of x2 minus f of x1. Okay, divided by x1 minus x2. This I'll say, let's suppose, we'll use Mahmood's name. Mahmood y by Mahmood x. Okay. So now you see that this x2 and this x1, there is a change happening over a duration. If you somehow could make it an instant, if you can somehow come up with a metric, if you can somehow come up with a quantification where I can make this change in an instant, I'll call that instantaneous change. That basically will give me the first thing that we'll study in the calculus, that's derivatives. Okay. So what I want now is, I want this x2, this should be equal to x1, but I'll add very small quantity which I'll call h. So this h basically is somewhere equal to 0.00000 somewhat 1, very small quantity. Okay, I want to quantify an instant, what I mean by an instant. So if I now write like this, so I have f of x2 minus f of x1 divided by x2 minus x1. This I called as Mahmood of y divided by Mahmood of x. Why did I call it this? I called it this because I was seeing the change with respect to something, and now I wanted this change in an instant. Okay, I want instantaneous change, but I said that this is total paradoxical. Now we have to solve this paradox. The paradox is that there is no change in an instant. If there is an instant, there is no change. Now mathematically we will have to say something about it. Okay, so what I did is I said, okay, I have this x1 and x2. So here we have x2, here we have x1. I said that once you are at x1, just make a small nudge. The nudge should be very smaller. That's called as infinitesimally small. As we have infinity, that is very big quantity. Then we have infinitesimally small, where we have the small quantity which goes near to 0, but it's not exactly 0. That's why we bring in limits. Okay, so what I said is here is, so what this x2 is basically equal to, I can write is f of x1 plus a little bit nudge, that's h, minus f of x1 divided by, so I know that x2 is a small quantity added to the x1. So here if you see x1 plus h minus x1, so you will just see that these two things will cancel each other, so I'll just get h over here. So now I had Mahmood y by Mahmood h. Okay, now mathematicians, what they did is they called this thing as dy by dx. The point is that this h should be infinitely small, which they call h tends to 0. They say that this h goes to 0. This they call as instantaneous rate of change. So they'll call this as instantaneous rate of change. I'm not talking about derivatives though. So I'm just talking about rate of change. The first thing is we talk average rate of change. So what is average rate of change? I took a huge big interval. So in that I saw, let's suppose we have this much distance traveled in the interval divided by total time taken. So I saw speed. Okay. Then I saw that, okay, if I want to see this instantaneous change that my speedometer reads. Okay, so how will you do it? So the ideally it should happen is that this h should be very small. The nudge that you make, it should be an instant. It should be probably 0.00, how many so ever zeros you can take. Okay, and at the end make it 1. It should not be 0, and it should be a small positive quantity. So this basically is the definition of derivatives. So here I have not introduced the people will write limit x tends to 0 f of this and that. So how many of you understood it without notations? Even how many of you have feel that we understood its physical meaning? It has a physical meaning associated with it. Nobody? Can you raise your hands if you understood the meaning of this? If you understood the meaning, I said this is about poetry. This is all about poetry. Poetry may take time. Okay, so again, where we started with rates of change. We started functions. Now I said that functions will change with time, or functions will change with something. Okay, we have a quantity which does not depend on time. Let's say which depend on something x. So as x changes, this y will change. So there is a dependency in that. So now I wanted to compute. I wanted to quantify this change. मुझे ऐसा टूल चाहिए था जिसकी मदद से मैं इस चीज़ को क्वांटिफाई कर पाता और मुझे देखना कितना चेंज हो रहा है. Okay. So how I did it, I said, okay, I'll define average rate of change. So what will be average rate of change? I'll take a huge interval. So I'll see in that interval कितना change हो रहा है, quantity कितनी change हो रही है. But I now was having a problem. If I want to compute instantaneous change, which I'll require at many points of time, let's suppose speed, it's nothing but instantaneous change. So what mathematicians does is they did one useful trick. They said that make this x2 very minutely greater than this x1. Then we landed at this. So we said that f of x1 plus h minus f of x1. So this is the value of at let's suppose 1 p.m. So this will be at 1 p.m. and even like nanosecond, not even nanosecond, whatever smaller quantity is possible there. So this is the value of that instant. Okay, and after that I divide it by h because this is rate of change. It's not just change. So this is change. So this portion over here is change. So this gives me the rate of change. How much it changed. Okay, and then I call it derivative. So from change I went to rate of change. So from this rate of change, I went to average rate of change. And from this average rate, I went to instantaneous rate of change.
I have a question.
Yes. Glad to answer.
Yeah, because first you told us that we do not say that the speed, we do not take instantaneous, and we don't say that, oh, this is
Hey, you focus on the question, man. Don't see the comments.
so you first told that we for example take an average. So we told about average, we discussed about average,
Right.
but now you are omitting that average. You came to our concept about instantaneous.
Yes. That I'm saying. I said that there is a paradox. Instantaneous means it should happen in instant. Instant means there should no change. So now we have to tackle this.
But the problem is why we did not take it instantaneous early was because we don't know whether it will be constant over time, because we change speed over time. We accelerate sometimes, there is something
Mm-hmm,
else.
mm-hmm.
But now you are taking instantaneous and thinking that it will be same for the whole quantity or for all the time.
No, 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 no. So why do I call this instantaneous change? Because I'm not interested in what happened in the whole interval. I am only interested in what is happening at that instant, as the
But
speed showed you.
it will be of no use if things are changing
Oh,
over
oh my
time.
God, oh my God. You are crossing the whole calculus. So whole calculus is dealing with this instantaneous change. If
Yeah,
there,
I know.
yes, yes.
Say suppose this time the x2 minus this x1 plus h is something, and over time because which we keep on changing the value of x. I mean, what
Mm-hmm,
was
mm-hmm.
value of x right now will not be after 1 hour. Suppose how would I say, in 10 minutes, say suppose in 10 minutes we covered 1 kilometer, so in next 10 minutes we won't be able to cover
Yes, 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 yes.
the
True,
same
true,
kilometer.
true.
So yeah, how this holds then?
So I'm not worried about average now. So what I said is I'm worried about if I have to compute something at an instant. So that's what calculus deals about. So it's not about like, yeah, we have to fit in this framework. So average speed is good. So if you give me an average, average is basically giving me a summary. But my point here is not to compute the summary. Sometimes I am in many of the problems I am dealing with the instant. I want to see what is happening at this instant. So but I said that this is some paradox. So if you have to compute change in an instant, so in an instant, how can you compute this change? Because change does not happen in an instant. So what mathematicians come with, they come up with the tools. Okay, if we had this f of x1, it will have some value. So we'll compute f of x1 plus some h. So this h will be a very minute quantity. Okay, this h where they write it, h tends to 0. So this is absolutely going to 0, and then we'll see how much change happened over this instant. Okay, again, this is just a way of dealing with this change in instantaneous. So that's what the fathers of calculus had the problem in head. Okay, how to deal with this instantaneous and change. Okay, but it has very useful implications. Whatever probably you are doing, most of the things they use calculus underneath the hood. Okay, probably if you have the doubt, we can have a separate discussion on this. But here, probably
Yeah, I understood. Yes, I understood. It.
yes, because there are many people and we cannot prolong the class. So I hope that everybody got this. We started with change and we said there is a rate of change. Okay, how fast or how slow the changing is happening, and then we said that there is average rate of change. Okay, in a big interval which we can quantify. So how much change is happening, and sometimes we are worried about instantaneous rate of change. I hope this is clear. So if something is looking like this, let's suppose we have a function something like this. So you see that the change that happened from here to here. So this much is the change. This is called as rise and this is called as run. Okay, sometimes you might be seeing books writing rise or run. So this is the change. If you see, so this much is the rise. The run is this much. So if you take the same run, let's suppose. So I'll take from here to here, almost the similar. But you see the rise is more now. So in this interval, so the change is less. So in this interval, the change is more. This the basically change is changing. Okay, the change itself is changing. How fast it's going. That's why we brought the concept of rate of change. So rate of change quantifies how fast or how slowly things are changing. Rate of change.
I think now I got clear.
Okay, so here if you see this run, so if you see this rise, so there is some change in that interval. So if I take the same run, but you will see the rise is more now, the change is more. So that's what quantifies the rate of change. Okay, and then a lot of things there we want to change at an instant. We don't want with the interval. And what we'll do is we'll make this graph is there, and now we'll make this interval very short. So if you just zoom it in, so there is this interval will be like this. So it will be almost a tangent line now, like this. That's why we call sometimes. So if you see the rate of change is defined by the slope. That is equal to slope. Why is it equal to slope? Let's suppose we had these 2 points. Okay, so this was our run, and now this much is our rise. So if you see, let's suppose the value was here, and this value is over here, and you see this much is our rise. So this is my rise, this is my run. Okay, I'm interested in the change basically, rise over run, rise divided by run. So if you make this a right angle triangle, okay, if you make this right angle triangle, so you know that this angle, let's suppose we'll call it a theta. Now I can write this is equal to tan theta. This is my slope. How I can write this also? So if it is if it is in coordinate geometry, so I said slope is basically equal to tan theta. This is equal to rise over run. So this is basically equal to change in y divided by change in x. So I can write it. Let's suppose this is my rise. This is y2. y2 minus y1 divided by x2 minus x1. So you will write it like something like this: delta x by delta y by delta x. So when this change goes to it tends to 0, okay, it limits to 0. That is how Mahmoud become d. That we'll write it dy by dx. When this basically this x delta x, this tends to 0. This is very small change now. So I'm just making these points sit together. So I'm probably making this point like this. So now you see that you'll only see the slope. You won't see the big triangle. So initially we saw this much big triangle when the interval was from here to here. So if I keep on decreasing the distance, then interval will be here from here, and you'll see this is there. And slowly, if you just have points which is on top over each other, you will see that this becomes slope. This is how we define slope. We define slope with tan theta. Why is it tan theta? Because tan theta is equal to perpendicular by base. So this is perpendicular and this is my base. My rise is perpendicular and run is base. That's why I wrote it rise over run. Okay, change in y divided by change in x. So I hope that many of the notations I introduced, are they clear now? Why is this tan theta equal to this? Why do we call this a slope? Okay, so this was the major thing that I wanted you to introduce to, so that you understood all these notations. So why is this slope equal to tan theta? And why is it equal to rise over run? Why is it equal to change in y divided by change in x? I hope that everybody got some clarity on these things now. Okay, now you can see that there is, let's suppose, I'll take an example. I'll take an example of time and temperature. Okay, daytime and the temperature. Let's suppose we'll start the day with at 8 a.m. okay, and then 9, let's suppose, then 10, 11, 12, then we'll change to p.m. something like this. So if you the temperature, so let's suppose there is 38, this is 40, and this is some 44, this is something else. So now you see that within the interval, let's suppose from 8 to 9, the change was 2. From 9 to 10, the change was 4 degrees. Now you see that here we have greater change. So now here we have less change. 2 is less than 4. In this 8 to 9, we had some change of 2 degrees. From 9 to 10, we had more change. Again, slowly you will see probably, let's suppose here the change will be some 10 degrees, something like this. Okay, it's pretty hot now. I'll write 54 degrees over here. And we want to compute this range. So this change was over an interval. If we make this interval very small, and we want to compute the instantaneous change. Okay, so how do we compute? So there will be a function which will be mapping these two quantities, which we, in generic terms, we wrote that like this: y is equal to f of x. So this x is probably time and this y is temperature. So there is some relation between these two things, which in technical terms we call a function. So if I have to compute rate of change, so I'll write f of x1, okay, and then I'll write f of x2. This is one value after which I want to compute the change, and I'll write divided by x2 minus x1. Okay, so this I call change in temperature. And then because of this, I'll call it rate of change. I want to see how fast or how slowly the things change, because I want in the same interval how fast or how slowly it change. So this is the rate of change, and I do not want to discuss whole the calculus here. Okay, I just wanted to give you
is it necessary that for this calculating the slope we need the interval? I get confused that the instantaneous and the interval.
No. This
Is this necessary for the slope calculation of the slope? We have to define the interval.
not necessary though. Not necessary. It's not necessary that you have to have an interval. For the slope, that's how we define it. So it's all basically on the definitions. So if you let's suppose do not define an interval. Let's suppose we'll see the linear equations. There you don't need to have an interval, because the rate of change is constant. If the rate of change is constant, then you will see that something is like this line. Line has a rate of constant rate of change. So there we'll directly say it slope. That's why I wanted to show you the beauty of maths. Just hold with me for probably 5 minutes or so. We'll use these linear models, how to fit these things to the data. So there I'll show you like why the slope is defined the way it is defined. I hope that you at least got the clarity of these things. So can I move forward?
I don't get the clear answer that what is the instantaneous slope and the what is this slope y2 minus y1 we can say, or x2 minus x1.
This is how we define it. This is how we define definitions basically. This is definition how we define the slope. What is slope? If somebody says what is slope, slope is rise over run. Basically change in rise divided by run. So you had some rise and you had some run in
You
the back.
use the instantaneous word that makes me confused.
No, but instantaneous.
I know the literal meaning of the instantaneous.
Okay.
That it is a some time,
Mhm.
but I got here confused that is this necessary to having an interval for the slope, or if we get the instantaneous slope, what is the condition there?
So
I
let's
get
suppose
little bit confused.
if you have, let's suppose you have a graph like this, okay, and you are saying what's the slope of this graph? Is this graph having a slope?
Yes.
It is not having a slope. The slope is continuously changing. That's what I'm saying. You should have a constant. The slope is for this. Let's say if you have a straight line, then we have a slope over here. This is a slope.
Okay. Okay.
So if we have some graph like this, okay, the slope is constantly changing. So at this point, this is the slope. At this point, this is the slope.
Okay. Got it.
I hope this was the confusion. Huh?
Okay.
Genuine doubt though. Genuine doubt. Okay. Nice that you guys are paying attention. I'm so happy that I'm getting questions. So now let us see something called as linear functions. Okay, it will probably clarify Abbas's confusion more. So linear functions. So what are linear functions? So now if this rate of change is not changing, okay, the rate of change is not changing. This probably may be a tongue twister. So if you see over here, you see this rate of change was changing again. So in this interval we had 2 degree centigrade change. In the same interval now we have 4 degree centigrade change. Now you can see the graph will look something like this. So which I showed. So graph would look something like this. Let's suppose change was like this, temperature was going this like this. Okay. So here you see in this interval, let's suppose how much was the change, and you will have a slope. Okay. Then for example from here to here you will again have a slope. Okay. This slope will basically tell you how much the change was there. Okay. Slope is giving you change. Now if you see that this rate of change is not constant or let's suppose over the whole period of time or the whole domain. Okay. We call such functions as non-linear functions. Why are they called non-linear? Because there is no linear relationship. So what my topic over here is linear function. What are linear functions? Where the rate of change is same. Where the rate of change basically is same throughout. So what are these functions? These functions will look something like a line. That's why they are called linear. Y is equal, let's suppose 3x plus 4. This will have a linear growth. Okay. So this will, if you take x1, if you take an interval, y you will take, let's suppose 1, 2. Okay, 1, 2 has a resistance 1, so you can write y is equal 3 multiplied by 1 plus 4, and this is my y1. So this is x1, this is my x2. I don't want to get the mathematical calculations, that's all right though. So y1 is equal to some 7. So here if I now compute y2, so y2 will be 3 to 6 plus 4 is 10. So the y2 minus y1, if you see the change over here is 3. And you see that change in the x was 1. So if I now go from 2 to 3, so this is my new x1 and new x2. This is my new x1 and this is my x2. I'll again compute this. I'll compute y of 2 and I'll compute y of 3. So what is y of 2 over here? So that's 10, which I already computed, I think. This is 10. So now if you see this, so this will be 13. So again, if you see that y2 minus y3 was equal to y1 minus y2. So if you see that we did the same change was there in the domain, the same change we shifted from 1 to 2, this was the interval. Then we shifted from 2 to 3. So now the change that happened here was 3 and the change happened over here was also 3. In both the scenario the change was same. If you keep the interval same, the change was same. So such a functions, which such a mapping, such a ruling, so we call these mappings, these functions as linear maps, or we call them linear functions. Okay, many of the real world things form this. So now we can write this in succinct format. So how we can write this? We can write y is equal to some a times x plus b. What is this a? This over here is slope. And this over here is called as intercept. These are just names. So if you see this slope over here, now you know that the slope is constant. Slope is not changing. That's why I can put this constant quantity over here. This is not changing. For linear equations, I have a constant slope. But if I have some non-linear like this, so you know that the slope is constantly changing. So I cannot put a constant slope over there. Slope is always changing over here. So if you see for these linear models, I can write things like this. So now let's suppose you observe a process. You observe a process, and then for the whole process, you know that some linearity is involved. The only thing that you have to find is this A and this B. Okay, I will call them linear models. Now, what is this function used for? So in day-to-day life, functions, they are used for modeling. You have a real world phenomenon, and then you have to model a thing. So if there is a process which is linear, okay, so what you can do is, there you don't need to give me the whole thing. You can just give me this A and B. If you are able to give me this A and B, I can tell you about the whole process. Why? Because we know that we can fit a linear model onto that. So what is linear model? We'll have to find a slope, and we'll have to find an intercept. So here if you see that, sometimes you might write y is equal to mx plus c. Okay, this m is slope. So how to compute the slope? y2 minus y1 divided by x2 minus x1. Okay, and this is my y-intercept, where the line cuts basically. If it is like this, so here, if my linear model looks like this, so this distance over here is my intercept. And you know that now the slope is constant. This is my slope. That's why I'm dividing it by x2 minus x1. So if you now take bigger intervals or whatever, so you'll get basically the average thing. So if you take, let's suppose, from 2 to 4, okay, and now then you take 4 to 10. Here you see that the change is now once we divide it, it will become per unit change. So here we'll see per unit change. So how many of you were able to see these linear functions? We'll take a physical examples in order to make this more comprehensible. Is it clear so far? अरे कुछ तो बोलो. Okay, let's take a physical example like this. Okay, हम लोग physical example लेते so that you understand it better. Let's suppose I have a tape. I have a tape with me. Let's suppose this is a bucket. Taking very vague example, but I hope that this gets the point through. Let's suppose bucket has some water inside it already. Let's say bucket has 5 liters of water inside it. Okay. Then I'm having a tape over here, which will put some water into this. Let's suppose I'll make this shows I missed my art classes. This is tape. Let's suppose there is a constant flow of water. There is constant flow of water. If there is a constant flow of water, what will happen is, so let's suppose this tape is giving 10 liters per hour. Okay, and I have to fill this bucket with the water, and this is a huge bucket, let's say. So this is a linear relationship. Why? Because you know that there is a constant flow of water. You can say how you can represent it. In the modeling, see how to model these problems now. Now you understood the problem. You understood the problem in the words. Now you have to fit the variables. Okay, what are the variables? You see that this variable is there. How much water is being fed into this bucket in what time, and what is the quantity that it actually was there. So let's introduce some variables. Suppose. So we'll say 10 liters per hour. We'll say the time. Okay, some time was there, and how much water. Okay, plus what was the initial water in there. Initial water. So this basically will tell me how much water is at time t. How much water is at time t. Okay, we are just counting the t as per hour. So this is water and multiplied by time, because I know that. Let's suppose if I have I have my tape on since 2 hours, so I'll just write 10 liter multiplied by 2. That is 20 liters will be pushed or pumped towards this, and I already had 5 liters in it. So now if you see that this has a linear model in it, so there is a linearity involved because the flow of the water is constant. So what is the equation I write? I can write equation y is equal to 20t plus how much water was initially there? 5. So this is what is the linear equation there. This is what I'll fit the linear model. This is my linear model. So if there is a real world phenomenon where you see that this flow is constant, this somehow will follow the linearity property. So you just have to give, so this over here is slope now. So in mathematical terms, this 20 is my slope. This 5 is my intercept. Okay, now again, if you draw the graph of this, so it will be somehow like this. Okay, somewhat whatever it is. So here you will see that this intercept will be 5, and this change will be somewhat 20. So 20 If I take from this to this, so this will be my, let's suppose, run, this will be my rise, so this rise will be 20. This is my slope over there. How many of you understood this now? With a physical example, there will be a lot of phenomena which will sort of follow this pattern, while we'll have something constant and the change will happen constantly. The rate of change basically will be constant. There will be no change in rate of change. The beauty
I'm
of
keen
maths
to
is,
look now. When the slope will be different, I will be keen to see that example now.
that is where the calculus comes in, because
Wow.
now you have these non-linearity things, and then you see the, oh, we have to deal with this non-linearity. Now there is the rate of change itself is changing now. So how to deal with that? That's what was the question that was in the hands of Newton, Leibniz, these people who were dealing with these change, because they were seeing there are a lot of phenomena, real world phenomena, which where we deal with these rate of change, and these rate of change itself change. So how to tackle with these? And they brought in differentiation, and then they brought integration. Even these fields were independently created. It's not that they discussed with people and then they did. They were tackling the problems and they independently chose it. And if you see the notations the Leibniz used and the Newton used, they're entirely different. Leibniz used this dy by dx. Okay, I think Newton used this f dash of x. But both of these people, they knew these techniques independently. They reached the same conclusions. Maybe the notations were different, but the gist, the thing that they wanted to convey was the same, because that's how maths work. There is so much beauty in maths. Why? So the other day I was discussing with somebody, just digression. If you see this pi, how is this pi defined? This pi basically is if you have a circle and it has a radius r. Okay, how is this pi defined? Basically, you will take the circumference of the circle, circumference divided by 2r. Okay, because we know the circumference is 2 pi r. So this is circumference. So if you have to pi, you just divide the circumference by that 2 times radius. So you have the measurement of radius and you have the circle over here. Okay, how do you define pi? This is the definition of pi basically. Definition of pi is circumference divided by 2r. So this is the definition. Take any circle and take its radius and then double the radius, basically the diameter. Circumference by diameter is the pi. This is definition of pi. So now we have circles. Okay, this is circles. And you know, somehow the heights of people are related to circles. So there is something called as Gaussian distribution, and heights of people follow Gaussian distribution. So in the formulation, you will see that 1 divided by under root of 2 pi. What has this pi to do with the heights of human? That is the hidden thing that mathematics found. There are hidden like patterns in the world. Okay, you are studying one quantity, you are studying about something, and then suddenly that same thing appears somewhere else. So you think, what's the connection between two things? That's the beauty of maths. The beauty of maths is that in whatever you can't explain the words, whatever you don't have words for, and then you will see a pattern over there. You will see one quantity has some connection with other quantity, and this pi appears so frequently in many quantities, and this just was derived by these from the circles and this, and that's how far we have went. That's why I urge everybody to study maths. Then only you will find the beauty. You will see that totally two unrelated things which has no relation in the real world. You will see some underlying pattern there. You will see them. There is a quantity. There is a mathematical thing which describes something like this. That's what poetry basically is. In poetry, let's suppose if I recite a poem over here, many other people from you, based on the experiences, will extract different meaning from it, because that's on the definition of what is the information that is with you. So if I say something, you related something. If I say something about love, everybody would get related to that because they'll have a story of their love in their own way. Okay, that's what maths is. So if you are from a field, let's suppose you are from a field of deep learning, so you will see this maths differently. If you are from a field of physics, if you are from, let's suppose, electrical background, you will see this maths differently. But you will see a constant thing there. That is, it defines processes unreasonably well. Sometimes it baffles your mind. See, oh my God, what happened? What just happened? So I just wrote an equation, and then I manipulated it. That's why the other day I was discussing the thing. There are two types of people. Just a digression again to motivate these undergraduate people to pursue maths. So there are two types of people. Okay, so I'll just make a dot. The first type of people is they see some real world thing and they try to quantify it. उनको एक quantification चाहिए उसके लिए. So they discover maths. This is one beauty of maths. You see a real world phenomenon and then you try to explain it and you use these equations, numbers, variables, whatever, and you try to explain it with the maths. But the second types of people are, they are not dealing with real world problems. So they develop maths irrespective of whatever there is. So they'll see some pattern and they'll just work on this. They'll work on this mathematical part. Sometimes probably they won't know it defines reality or something. Then there are second types of people which take this abstract math and they will somehow map it to a real world problem. So one type of person is that they'll have a real world problem, quantify it, bring in the maths and explain the process. And there are another type of people. So maths major lie in here. They don't care about real world because they know that somehow this math explains reality. Probably I am the one who has the problem. I'm not able to sort of find a problem which maps to this mathematics. But anyways, I'll create this mathematics. It's all right. Okay, and then somebody will come and see this in the real world. They'll map this problem. Okay, if you see Einstein, what did he do? So he predicted black holes. He predicted gravitational waves by using this mathematics only. Then people, some experimentalists, which were experiments, and they found the gravitational waves. Many other things that you are doing, the cryptography. There were enthusiasts which were doing number theory. They were just seeing pattern in numbers. They were seeing some pattern is there. Okay, and if you multiply this number by this, there something happens. If you take modular arithmetic, something happens. And nobody has an idea where it will be used. Then people once because they had this maths developed. And after that, what happened is suddenly people, when they got mobile phones, then they found a need of security. They use the whole number theory there. So okay, so one person is having real world problem, quantifying it by using mathematics. Other person, which usually are maths majors, so they'll do this abstract stuff. They are not caring about real world problem. They'll bring in the maths. If maths predicted something, so probably they want to see it. Okay, where is the real world? And the whole quantum mechanics, if you see, it was predicted by mathematics. Mathematics said something. Okay, but equations say something. There was like the thing that I got baffled about was these entanglement states. It was predicted wholly by mathematics. Mathematics said that there should be these states which should be entangled. There is no possibility that you can decompose them. And in the real world, it was counterintuitive. We were thinking that this should not happen. But mathematics is always right. Intuition is sometimes very wrong. That's the beauty of maths. So maths takes these problems sometimes and bring it in the real world. And sometimes what will happen is you will have these mathematics and it will somehow map to the real world. Let me pause here for a second. I'll drink some water. You know the language of mathematics now. You know a little bit, some vocabulary you have now. You know what a domain is, what a range is, what a function is. You have this vocabulary. On this vocabulary, we'll develop it. But I'd love to develop it from the graphical point of view. And then you'll have to think. Let's suppose I have a function like this. Okay. Let's suppose I have function something like this, parabolic function. Okay. Now this is defined by something by y is equal to f of x. Okay, so what if I want to shift these values? Okay, I want to show you how shifts happen. So you can just move it here. They're called transformations. The whole of this computer graphics is basically transformations. You have a function, you are transforming it in some way. So how do you do these transformations? Okay, so you have a function basically y is equal to f of x. This is a function, generic function. I'm not concerned about. Let's suppose you have some object there which is described by a function. Let's suppose you have a ball. This ball is basically just a function. It's nothing but a function. Give me a second as somebody is calling. Okay. So what I was saying is I was saying that this circle basically it can be represented by using you can have a mathematical equation which will sort of have these points define this in the computer's memory. So we have whole of this 3D modeling. So we can use point cloud. You can use what's called as meshes. I don't want to get into those details. How do we represent this in computer memory or how do we represent this in memory? That's all right. But there is something associated with it. So what I'm saying is that if you want to shift these objects here on the screen, okay, you have to make vertical shift, you have to make horizontal shift, you have to align them somewhere. Okay, what you can do is, so you basically just manipulate these functions. There are some matrix multiplication, something you will do. Okay, then you will see everything that's happening on the screen is nothing but mathematics happening behind that. Okay, a whole of this is studied under what is called as graphics and visualization. Then you see this ray tracing, rendering, all of this stuff. That's why I wanted to show you there is some quantity which is related to a function. There is a mathematical equation. How to shift these graphs now? Okay, these are called transformations, and they may be linear transformations. Some transformations are called affine transformations. Don't get into these terms. We'll slowly see these terms also. So in the transformation, we first would like to see the vertical transformations. This vertical transformations. So if you have a function y is equal to f of x. So this function could be like this. Let's suppose y is equal to x square. This is a function. So if I just want to move it a bit up, so what I can write is I'll say y is equal to f of x plus this constant. So what will happen is, so this probably will go here. Okay, so we can also try it in Desmos. So I showed you that tool. No need to just compute the value. Just use that tool and see if in actual if there is a vertical shifting or not. Okay, you can see that clearly. So here you will see that I'll just add some constant to this function value. So it will horizontally shift it because this is the y value. If I want to shift the y value, x value should remain the same, but I should just add something to it and it will go on to this. So this is the vertical shifting. So how to make a horizontal shift? So how to make this horizontal shift? So if I have graph, let's suppose something like this, anything like this. So if I want to shift it, maybe right or left. So what I'll do is I'll say I know y is equal to f of x. So what I'll do is I'll just say y is equal to f of x plus something. So I'll add some c over here. Okay, you will see that it'll shift over here. It'll shift. These things will shift. These graphs will shift. The function basically remains the same, but you are just making shifting. Sometimes you want vertical shift. Sometimes you want horizontal shift. Now you can create any shift in 2D. You can shift it anywhere. You'll just use the combination of these things. So you can use y is equal to f of x plus some c1 plus some c2. So this will make any sort of shift that you want on 2D. This can make shift in horizontal direction, in vertical direction, maybe some slanted way, wherever you want. You just have to change these constants. Please and please do use this Desmos calculator where you can just tinker with these things so that you get this properly into your brains and you understand this very well, because this is really important when you are doing machine learning, when you are doing these stuff. And there you'll have to imagine these things. Okay, I'm just multiplying this by the constant. What will happen? I'm just adding something to it. What will happen? I'm adding noise to an image. What is noise basically doing? Okay, I'm just subtracting noise. So if you see diffusion models, so there what you do is you basically subtract noise slowly. So you take a picture and then you will subtract this noise, and slowly you will see that a picture of dog appeared. Okay, the whole of thing you should have this clarity over here, that how to shift these functions. Okay, now you see this horizontal shift, you see this vertical shift. How can I shrink these functions? How can I shrink properly? I want to shrink these functions. Let's suppose my function is like this, and this function is like this. So I want my function to be same, but it should be a smaller version of this. So what I can do is, I know that my function is y is equal to f of x. So how to shrink it? So you can just say y is equal to f of some c times x. I don't want to give the intuition. I want to think about these things. Otherwise, I would have told you the intuition. Please do come to me with questions. So whatever I'm writing now you have to think about a graph and just add something to it, subtract something to it, and see what will happen. See if it stretches, see if it probably gets shrinked, or see if it moves here and there. So I showed you vertical movement, how we can do vertical movement. How can we do horizontal movements? How can we shrink it? Okay, how can we expand it? Okay, you just have to multiply with the constant. But this will be really important once we are at that topics, once we have to imagine these things. Then once you have these things done, once I'm saying you, okay, I'm adding some noise. So somehow you should map it to here. Okay, there's a function, we're adding noise, that means we're shifting it some way. Okay, this is the thing that I wanted to introduce for that models, for these things, because these concepts are really important once we go there. Okay, now we'll go to one important aspect, what's called as invertibility. Because today I want to somehow close this function so that you guys are apt with the concept, so that you can start with your assignment 0, and then we'll move on to probably real calculus or something like that. So uske baad you'll appreciate all the things that we did so far. Probably this might look basic to many other people. Okay, I know that we have postgrads here and we have PhDs here. This may look very basic, but once you delve into these things, you understand the details, then you will really appreciate the things that we are going to do in the future. Okay, what is invertibility now? Now you have a function. Okay, you have this function y is equal to f of x. Okay, so now what you want is, you want some inverse relation. You had this independent variable and you had this dependent variable. Okay, so you want to undo the change. I said that we have a machine is a function. Okay, you take some input, get an output. So what if I want a machine for which I'll give an output like this? Okay, and then it should give me corresponding inputs. So this is my setting. This is what I want. I want to build a machine in such a way that if I give the output, somehow this machine should process, it should give me back this input. So a reverse process I want to do. Now you know how we define functions. We define functions like this. So there should be, so if you have we call as pre-image over here. So for that you cannot have two images. So this is not allowed in functions. Now to have inverse of a function, the same thing should happen in the backwards. So why should same thing happen? Because that's by definition of functions. So if you see it over here, so I want my functions to look something like this. So if you have some things over here, so they should have a mapping over here also. So this should not be like this also. Okay, so this basically is not function. So now if I this is function. So if one element and if second element is mapped to the same element, this is a function. But for invertibility, if I have to reverse it, because now I have to make this as pre-image and this as image, so this should not be allowed again. Now we are putting constraints. If we have to find the inverse of the function, then at least one constraint you can see clearly over here as of now, because this is a valid function where we can have two inputs and they'll have the same image. But once you invert the thing, you will go out of the definition of the functions. So now we are restricted by the thing that if you are computing the inverse of a function, this should not happen there. This should not be there. Okay. So this property is called as 1-to-1. So what is this 1-to-1? So each of this pre-image has only one image now. So they'll have this, and they'll have this probably, and they'll have this, they'll have this. Maybe one element is there still. So this is 1-to-1. So I want one more property for the inversion. So I said that this is called as, this is my codomain. Okay, what is codomain? The whole thing over there. So maybe there are some undefined elements, but when I invert the things, so this should not be there. This stray element should not be there. So now I am again forced to do this thing. I am forced to do one more thing, is that whatever was there in the range, okay, whatever was there in the range, it should again be in the domain of that thing. It should be again in the domain of the function. So now this element, stray element, should not be there. Where there are not stray elements, this is called as onto. So my function should be 1-1 and onto. There should be 1-to-1 mapping, and it should be onto. Don't leave any element behind. Okay, then only the function's inverse will exist. I'm just telling the technicalities. This is y is equal to f of x. So how to tell you that if this f of x is invertible? Can you really invert it? Can you really undo the mapping? Whatever you did, so can you really undo it? So why is this again important? I'll again map this in linear algebra. There are some transformations where you cannot undo them. Okay, let's suppose you had a vector like this. Okay, so you perform some transformation. So there is no way possible where we can undo that transformation. So let's suppose you move this transformation over here. You can clearly see that this can be undone. You can just bring it here. But there are transformations which are not invertible. Okay, linear algebra is nothing but fancy functions. I'll make sure that whenever you study linear algebra, you will see that everything is a function there. So what I'm saying is, now you have this y is equal to f of x. The first point I'm saying is that if you want this function to be invertible, so what should happen is it should be 1-1 and it should be onto. Basically, it should be bijective, what they call it a bijection. It should be a bijection. The first thing is it should be 1-1. Why should be it 1-1? Because the problem is that if you just want to invert it, if it is not 1-1, so some one element, when once reversed, this is the condition that we'll get into. So there will be this two elements. So this element is mapped to this element is mapped to this. This is our function. Let's suppose f of x. When you want to find the inverse of this, now this will violate the definition of the function. That's why we want our function to be 1-to-1. That should be 1-to-1, and we want it to be onto also. What is onto? There should be no stray elements left over here. Why? Because otherwise we'll make the function undefined on those numbers. So these are two conditions for the invertibility. So I can write now the conditions for invertibility. Conditions for invertibility. The first condition is function should be 1 and 1, then function should be onto. Basically, function should be a bijection. So how do you how do you show that? So if this is y is equal to f of x, so we write f inverse of x, something like this. F inverse. This is the inverse of the function. So what is the effect of inverse? Inverse basically undoes the effect. Okay, if we have computed f of 2 is equal to 5, so we'll take this 5, we'll say f inverse of 5. This will be equal to 2 now. This is inversion. In very basic terms, all these questions you'll probably do in the assignment and stuff like that, but here I won't get you the intuition, what do I mean by invertibility and why is it used. Okay, some functions are not invertible. Okay, there you have to be very careful. If you make a transformation, you cannot undo the transformation. Okay, it maps it to something else. Okay, and that's why we call it linear algebra. So there we have linear transformations, and some linear transformations are not invertible. That's why this matrix inversion comes into picture. Why is this matrix invertible or is this matrix not invertible? I'm just giving the breadcrumbs so that you have these concepts in the head. Okay, this is the concept of invertibility. Okay, now you know the whole lingo of the things. Now you have, I told you have mathematics. Now you have to perform operations. This is mathematics, this is operations. Now I taught you the language of mathematics. Somewhat language of functions, you know, domain, range, sets, relations, intersection, whatever that is. And now there's operations, this plus, minus, multiplication, division, these are defined. Okay, so you can do all these operations with the functions. See the beauty of maths again. If you were talking in the verbal of things, you cannot add these two verbal things. Let's suppose I say that something is dependent onto this thing, then this, probably you can, but it will be too tedious. Okay, I can say, let's suppose a function y is equal to f of x, and there is some function, let's suppose g of x. I can add them together. F of x plus g of x. So this is some real world phenomenon. This is again some real world phenomenon. Okay, I'm adding them in some way. This is the power mathematics gives you. Okay, verbally, there probably you won't understand what is the meaning of addition. In the whole thing, what is the meaning of addition? Now, if you have a process where you see that you have these multiple functions, that's where when programming came in. Okay, we say that there are procedural programming. That's what these procedures are. You just combine these functions together. You write a function, then you write some other function. You call function within a function. You probably call function sequentially. The whole problem is that one function does one thing, other function does other thing. If you want a combined effect, so combine them together. Okay, and the ways of combination are different. You can combine them by using addition, by using subtraction, multiplication, division, and there is one more combination thing. You can use what is called as composition of functions. These are the operations involved in functions, the operations that are allowed on the functions and that make sense on the functions. You can add two functions, you can subtract two functions, you can multiply two functions, you can divide functions, and you can take composition of function. One more operation over here. Numbers, you can only do this much, you cannot do composition. You should think maths in this direction. You should not think maths like something is defined, I'll have to read it up. No, you now develop the lingo, you should see, okay, what are the operations that are allowed on these now? I said you that you can add two functions. So how to add these functions?
Please give a light on this composition.
Yes. I'll do that. The template that I want to give you is somewhat different. I told you on the first day, I am not here to per se teach you the concepts. I am rather teach you how to think. So here we developed mathematics language. We developed a language of functions. And then I said, on this language, we can now perform operations, which is rarely possible on the human language that we speak. So what are the operations? I said, these are the operations which make sense. Okay, sometimes some operations may not make sense and some more operations may make sense. Okay, I'll take the addition first, how to add the functions. Okay, we'll start with the addition and then we'll go subtraction, division, and then we'll go on the composition of the functions. So how to add these two functions? So if I have, let's suppose, one function x square, we have y is equal to x square. Y is equal to x square. So I have some other function y is equal to 3x. On adding these two things, what I'll do is I'll say y is equal to 3x plus x square. This is how I add it. It perfectly makes sense. But one thing that you have to now take care of, now you have to see what is the domain of the function and what's the range of the function, because these things will get affected. This domain and the range will get affected somehow. The domain will not remain the same. The range will not remain the same. Now this is the homework for you. To see if I add two functions, what will happen to domain and what will happen to range. If I do now subtraction of the functions, what will happen to the domain and the range? Yes, any questions?
But we are talking about linear functions. Is this a linear function?
This is not a linear function. We're not talking linear, we're talking about functions in general now. The function, basically whatever we taught, that is functions. Now we are seeing what are the operations possible on those functions. I don't see why do you think in haphazard direction. That's one problem in maths. The thing is that linear functions, we talked about something, there are linear model, there is a function. But here again we're talking about two different functions. Now we have two different functions explaining two different phenomena. Or maybe they're explaining two things of a same process. Now you want to combine them together. I said how to combine these things. There are operations possible on the functions. Okay, but doing operation changes this. So they'll change the domain and the range. Now your work will be to see if I add two functions, what will happen to domain and what will happen to range. Okay, again I can subtract in the similar fashion. I can multiply in the similar fashion. Now the important thing is composition of the function. This is one more operation that is not available with the algebra. You had plus, then you had subtraction, you had addition, subtraction, multiplication, division. So one more I said is called as composition. So sometimes what will happen is you will have a machine, let's suppose. A machine is there, it takes some input, it gives some output. And this output is taken input by some machine 2. So this is machine 1, this is machine 2, and then it gives output 2. And we are concerned about this input and this output. Okay, and there will be multiple machines probably. Similar, you know that machines, some of functions work in the same way. If you have a function which takes f of x, this is the function. And then we have some other function y is equal to some f dash, maybe f1 of x, something like this. Okay, I'll call this f2 of x. We have two of these functions. Okay, if we have function f1 and we have function f2, somehow if we apply this function first and then we apply this function, rather we'll let f of x and g of x. These are two functions I have, rather than this f1 and f2. So I have these two functions, f of x and g of x. So if I want to combine these two, so sometimes I can write f of g of x. So what is the meaning of this? So the meaning of this is you will apply g first and then you will apply on top of the output of g, you will apply f. So input, you will give directly to g, so g will receive input g of x and this will give some output. So over here, this will give some output. And then this output will get into f. Okay, so this is called as f of g. And then reverse you can also do. You can do g of f also. You can first apply f and then on the output of the f, you can apply g onto that. And you can do it any number of times. That's why it's called composition of the function. You compose them together. Now you see that plus does not do it. Subtraction does not do it. Division does not do this. Okay, even multiplication does not do it. They have different notions what they do. But this is what you can do with functions. That's why we invented one more operation. We call it composition. That will happen in all the maths. You will have a language and it describes some problems, and then what will happen is you'll have to define operations. Sometimes some operations won't make sense. Even for some, like let's suppose we'll develop say some abstract maths. Let's call that Mahmood math, something like that. Okay, and that there this addition won't make sense. There addition of two quantities won't make sense. Division of two quantities won't make sense. But something else will make sense. Maybe mixing of quantities will make sense then. Then you have to come up with the operations accordingly. Okay, you build the maths for that, and you have an operation for that. Okay, you will apply these operations on the quantities. How many of you got this clarity of the language and the operations? This is just a vague way to explain you. So what are we going to do? Basically, we are just people on the hunt of maths. We want to see, okay, we want to develop a language and we want to build operations. And that we are doing it. Again, some people have done it. They already have the maths of these functions, and they already have the maths of these operations. Everybody with me? You can take that usually called as sum of functions, difference of functions, product of functions, quotient of functions. And one more is, they are not even called addition, they are just symbols. So here they call this sum of functions. This is called a difference of function. This is called as product of function. This is called as quotient of functions. And this is called as composition of functions. There are different names for this. The symbols probably are from the algebra. Okay, this one more symbol, this O symbol is called as composition of the function. There is nothing to talk about functions anymore. This is it. This is functions. If you understood this, you are more than, I'll say, weaponized, and you are more than competent now to solve different questions. But now it will take your thinking. Now you can take these function thinking to any realm. You can now study polynomial functions. You can now study trigonometric functions. You can study, I'll say, almost everything that is there in functions. Okay. Now you have the basic lingo clear with you, and you have the operations with you. Now you can study what I call as trigonometric functions. You can study polynomial functions. And there's something called as equational functions and things like that. There are a lot of things that have been done. But this is all that I wanted to cover in the functions from my side. So I'll close this functions chapter. And now these are the breadcrumbs. It's your turn now to turn the page of these books and to think a lot and to fit every realm with the functions. Okay, whatever you see the physical phenomenon, can I make a function out of that? Okay, that's now you're thinking. I have just given you the language, and I have just given you the operations that you can perform on that language. Now just look at into the real world, go outside and see if there's a physical phenomenon where you can map it with the functions, and you can bring in some different signs out of that. Okay, I'll stop recording over here. So I'm willing to take your questions, and we'll have probably further discussions on these things.
And